Electric vehicles are everywhere now, right? But what's actually going on inside that giant battery? It can feel like a total mystery. Well, today we're going to pop the hood, so to speak, and trace the path of energy from the plug to the road, and believe it or not, back into the battery again. Let's get into it.
So let's kick things off with a question that really gets at the genius of EVs. You're stuck in traffic, inching forward, and you're thinking, this is just draining my battery. But what if I told you that traffic jam could actually be giving you free miles? Sounds impossible, right? Almost like magic. But it's all science, and we're going to break down exactly how that works. All right, so every EV journey starts in the same place, plugging in. This is step one, right? We're taking all that power from the grid and literally cramming it into the battery so we can use it on the road later. And the star of the show, of course, is the lithium-ion battery. I mean, at its heart, it's just a box to store energy. But the real secret sauce is how it does it, this incredible back-and-forth dance of tiny little particles called lithium ions. A good way to think about it is like a super efficient hotel for energy particles. So if we zoom in on a single battery cell, you'll find four main characters. You've got the cathode and the anode. Think of these as two different neighborhoods. Then there's the electrolyte, which is like the highway system connecting them. And finally, the separator. This is a super important one. It's like a traffic cop that makes sure the ions go where they're supposed to and prevents a massive short-circuiting pileup. Okay, so you plug in your car. What happens? The charger sends in a jolt of voltage. This basically tells all the lithium ions, all right, time to move. They pack their bags, leave the cathode neighborhood, cruise down that electrolyte highway, and check into the anode neighborhood. And every single ion that makes that trip is basically storing a tiny packet of energy. That's how the battery fills up. All right, our battery is topped up and we're ready to go. Time to hit the road. And as you probably guess, now we're just going to do that whole process, but in reverse. We're going to unleash all that energy we just stored. So you put your foot on the accelerator. The motor starts screaming for power. And that's the signal. The ions get the message. Time to go home. They start flowing back from the anode where they were vacationing all the way back to the cathode. It's this huge rush of ions moving in one direction that creates the electrical current. And that's what spins your motor and makes the car go.
And this right here, this is the whole game. This two-way street for the ions is everything. Charging is just pushing them one way to store energy. Driving is letting them flow back the other way to release it. It's this simple, elegant, back-and-forth chemical dance that makes the whole thing work. Okay, but let's be real. We don't drive our cars in a perfect lab. Out in the real world, things like how you drive, or even just the weather, can have a huge effect on your battery. This brings us to the idea of load. So let's talk about something called the C rate. It sounds technical, but it's simple. It's how fast you're asking the battery for power. Just cruising along, that's a low C rate. But when you floor it to get on the highway, you're demanding a super high C rate. Now look at the graph. A high C rate, like that green line, actually gives you less total energy. Why? Because you're forcing those ions out so fast that the battery heats up and wastes a bunch of energy. It's like trying to chug a drink too quickly. You end up spilling some. Same idea. And temperature. Wow, this is a big one. This graph really shows you just how much batteries hate the cold. At a comfy 23 degrees Celsius, you're getting everything the battery has to give. But look at that purple line. At a freezing -20, you're getting barely half the energy. It's crazy. The cold basically turns that electrolyte highway into thick sludge, and the ions just can't move as fast. It's a chemical traffic jam. Okay, so we know how to store energy and how to use it. But what about all the energy that normally just gets wasted? Well, this is where things get really cool. And yeah, this is where we finally answer that question about getting free miles from a traffic jam. This is all thanks to something called regenerative braking. See, normally when you brake, all that forward momentum, your kinetic energy, is just turned into useless heat. It's completely wasted. But with this system, your EV does something brilliant. It captures that motion and turns it back into electricity to recharge the battery. Let's put them side by side. Your old school friction brakes? They're pretty dumb energy-wise. They just squeeze brake pads on a disc. All that does is create friction and heat. Poof, the energy's gone. But regenerative braking, it's genius. It flips the electric motor into reverse, so it acts like a little generator. So you're slowing the car down and you're putting juice back into the battery at the exact same time. So does it actually make a difference? Oh yeah, a huge one. In stop-and-go city traffic, you can get back up to 30% of the energy you just used to get going. And there's your answer.
That traffic jam isn't just wasting your time anymore, it's actively putting miles back into your car. Now, this amazing back and forth dance can't go on forever. It's not perfect. Every single time you charge and discharge, the battery gets a little bit older, a little more worn out. So let's talk about the long game. How long is this battery actually going to last? Battery life is usually measured in something called cycles. Now, one cycle is basically using a full 100% of the battery. It could be one big trip from 100 down to 0, or it could be using 25% 4 times. But the key thing to remember is that every cycle takes a small toll. The battery's maximum capacity, its ability to hold a charge, goes down just a tiny, tiny bit each time.
So when is a battery officially old? Well, the industry has a rule of thumb. It's when the battery can only hold 80% of what it could when it was brand new. Now, it's not dead, it still works just fine, but you'll definitely notice that your range isn't what it used to be. So when people talk about cycle life, they're just counting how many of those full cycles it takes to get down to that 80% mark.
And this graph shows you exactly what that looks like in practice. See? It's not like the battery just falls off a cliff one day. It's a slow, gentle slope downwards. You can see here that after about 500 full cycles, a pretty typical battery has lost maybe 10–20% of its original capacity. It's just a slow, predictable process of getting older. Okay, this chart looks super complicated, but don't worry, the idea is really simple. Just look at that red circle in the middle. That's the sweet spot for a long, healthy battery life. Everything else, all those points, are things that stress the battery, and the farther away from the center they are, the more they shorten the battery's life. So you can see things we've talked about, like fast charging or extreme temperatures, really push things out and hurt the battery's lifespan. It's a great visual to show that it's not just one thing, it's a balancing act. So let's wrap this all up. What did we learn? First, charging and driving is just a two-way street for lithium ions. Simple as that. Second, how you drive and what the weather's like, they have a direct impact on your range. Third, regenerative braking is an awesome trick for clawing back energy that would have just been wasted. And finally, your battery's long-term health is all about balancing its design, how you use it, and the environment it lives in. And that leaves us with one last big question to chew on. We've seen this incredibly complex dance of physics and chemistry going on inside what looks like a simple box, but knowing that every cycle causes a little bit of wear and tear, is a battery that lasts forever even possible? Or is that slow fade just a fundamental part of the deal? It's something the brightest minds are working on right now.